And it turned out that the rigid body was exhibiting pitch oscillations, and he used Poincare sections to conjecture that the pitch oscillations were because of chaotic behavior. And he basically said that there are certain regimes of rigid body inertial parameters where the pitch oscillations exhibit chaotic behavior. And this also follows from a lot of the stability analysis work that Debray and Delp did, and followed up by Kane and others. And Kane actually says that this pitch oscillations are actually dependent on the initial attitude perturbation. So I'll set up the problem and you know what I'm talking about. So we wanted to see what is happening, because in that problem, even in the pristine condition of approximating the gravity gradient just with the first order terms, we are supposed to have a conservative system, and the fact that there are chaotic oscillations is not a good, it doesn't sit well in terms of modeling the problem. So we want to investigate that. So let me talk about that first. And the fundamental insight that it is a conservative dynamical system actually helped us prove or disprove that there is any chaotic behavior. It was not a chaotic behavior, it was just an energy exchange between the modes of the rotational degrees of freedom. And actually attitude dynamics is essentially decoupled as two coupled oscillators. There's two main oscillatory degrees of freedom, and they exchange energy, and that's what happens in these specific areas in the parameter space of the inertia. So that's the first paper. And it had the fact that these dynamical systems have these properties frequently helps us in many other aspects. So the second half of the talk is going to be exploiting the same fact and the same insight that there are some conservative properties, and the mechanics helps us to fuse measurements and so on and so forth. And how do we do that when only partial measurements are available for the dynamical system? How do we realize and bring physics together with data? Is the second part of the talk. And so that's essentially where we're going with this. Back to this is what I just mentioned. I'm going to skip this. So we wanted to study the gravity gradient on active motion and understand the nature of oscillations and characterize the stability of the equilibrium point. And we actually proved that there is not just one equilibrium point, there are many. And it is actually drastically different with different approximations of the gravity gradient potential. And that really begs the question as to whether the high order approximation of gravity is essential or not. And our recent paper shows that it is. So this is the setup of the problem. That's not a point mass rotating around the Earth. It is actually now a rigid body, and the coordinate systems are defined as the same frame that John used yesterday: radial, tangential, and normal, or the normal coordinate system. And about this coordinate system, we use a body frame, and the attitude of the body frame with respect to the orbit frame is the attitude that we are interested in. And we can, traditionally, Debray, Delp, and also Kane parameterize that attitude as a P12 Euler angle rotation sequence, P21. We decided to use a different route. We wanted to use Cayley transform and modified Rodriguez parameters to parameterize the attitude. The reason for this becomes clear in just a second. And modified Rodriguez parameters, these are Cayley transform parameters, these are the regular ones. These are basically the ratio of the vector part of the quaternion divided by the scalar part, basically. So that's what these are. So they are basically the principal vector times the tangent of half the principal angle. And what we do then is we take Euler's equations which are forced by now the gravity gradient of which is also an approximation. And we replace omega with basically the transform, which is a function of the attitude times the rate of the angle. Substitute that, and omega dot then becomes a function of dq double dot, and then we get an oscillator equation. And that's one of the things that's new that we have done. This is not available in the literature. We'll come back, I think. Okay, so this is the process. This is the attitude, the gravity gradient torque. And we do something else that John and also David Siliberto did yesterday in his paper. We actually not only do some differential equations in time, but also convert it using constants of motion. So we actually go to a fictitious time, which is the true anomaly, using the two-body problem. Okay, so this actually helps us a little bit. So actually what happens then is when we put these in there and do the math and dust settles, we get the second order differential equation that looks sort of familiar. The right-hand side, although it looks like a mess, right now it's not really. It's actually polynomial. If we had we used Euler's equations, we'd get a lot of trig functions in the right-hand side. So in a typical analysis problem of a nonlinear differential equation, what do we do? What is the first thing we do when we are dished out a nonlinear differential equation? Can somebody tell me what is the first thing we do? Anybody? What is the first thing? I mean, let's say I give you a Duffy oscillator. X dot is x double dot is minus x minus epsilon x cubed. What do I do then?
Find the equilibrium space.
That's the first thing we want to look at. Professor Junkenstock had something similar. So if there are trig functions, the right-hand side has transcendental equations, which can only be solved numerically, and Professor Junkenstock had the same thing. However, this equation is now polynomial in nature, and that we have some chance of actually solving it. This is a coupled three oscillators that are coupled on the right-hand side, but all kind of cross terms. Now, if we linearize this and assume that pitch degree of freedom, which actually turns out to be a function of the third component of the classical Rodriguez parameter, for a small angle, then we actually are left with Q3 double prime is equal to this mass. And when we set the right-hand side of that mass to 0, we get a quintic equation that's governing the roots of the right-hand side. Of course, this is not really useful right now, but this is the solution. So if we wanted to characterize the roots, we could just take the root locus of this quintic equation, and those are the roots of the problem. However, this process is not valid to analyze this differential equation because the coefficients are time dependent, or coefficients are a function of the independent variable. So we can't really say anything with the roots of this right now. However, if we fix ourselves to a circular orbit, it becomes a lot neater. And that's what we did next, of course. So in the special case of the circular orbit, and I want to point out that this special case of a circular orbit was the case that Randolph and Kane were looking at. So the orbit is circular, and they basically showed that oscillations had some behavior of pitch oscillations especially. Now, in that case, the horrendous differential equation I showed earlier actually boils down to this guy. All right? And K is a parameter which is a ratio of the inertias of interest. And when we actually set this to 0 and decouple the pitch oscillations, we get something simple. But even before that, my student actually solved it closed. So if you just do the pitch oscillations and write out second order differential equations, then he actually said that, okay, this guy has a constant of motion. That's the constant of motion. And it looks strangely like the simple pendulum. But the only approximation we make in arriving at this constant of motion is that the pitch oscillations are can be separated from the whole yaw degrees of freedom. In that case, we actually have a pendulum. This is a glorified pendulum, if you will. It has some extra rational function instead of just having the q dot squared, the kinetic and general potential energy. And if we use Euler angles, we get something like this, and that's the constant of motion case of pitch. And this was arrived at by linearizing this equation. And we didn't have to linearize; we just had to decouple and set the rho yaw oscillations to 0, and we had the same constant. So if we plot the level sets associated with that constant, it takes this form, and there are some specific values for these points where things go around and so on and so forth. So, but if you are below, I want you to note magnitude of that point. So if you are below this 1 radian initial pitch amplitude and 0.3.4, the motions are proved to be bounded. You can't have any oscillations. Now, because now we have a different differential equation that is easier to analyze, we can now go back and trace the stability. We can go back and trace stability analysis. And according to the traditional stability analysis that uses linearized equations of motion, we know that this region, the Bldg region, is linearly stable, and the Lagrange region is known to be stable. However, when we do the nonlinear analysis using the nonlinear differential equations, I'll explain to you how we do that. What we do then is we take the nonlinear differential equations, because even the coupled version, we start from the equilibrium point. Here is the origin. So the origin identically satisfies the right hand side to be 0. So when we substitute origin, these are supposed to be stable. So we then numerically integrate small deviations from that equilibrium point, and basically calculate the state transition matrix associated with the differential equations, and then measure the largest value of the state transition matrix and divide it by the magnitude of the state transition matrix of center point. We take all of the initial conditions around that around the equilibrium point, and if they remain at the bounded distance, the maximum value is below the bounded distance, we declare that to be a stable region. If they are not, if they increase in value, let's say 100 times or 1,000 times, then we declare that to be an unstable equilibrium point. So the Lagrange region has always been known to be stable, but we have identified, if they are linearly stable, we have identified some areas where the linear stability is not valid anymore because of the nonlinear definition of the stability. And these are the results. This one is that if we pick up some parameters from that, and we see these patterns of sudden increase in oscillations in the rho yaw, and the pitch oscillations decrease. And these decrease of pitch oscillations were reported to be chaotic behavior because they were unpredictable. If you look at pitch oscillations alone, you cannot really tell when it will go down, when it will come back up. And that was declared to be chaotic by the previous authors. We immediately, when we looked at the coupled equations, because we have a simpler form of differential equations. So what we noted was that it was just an energy exchange between the pitch degrees of freedom, pitch degree of freedom, and the rho yaw degrees of freedom. You can kind of see that. So whenever this goes down, that energy gets pumped into this, and this pitch oscillation goes down, and the energy gets transferred into a different degree of freedom. Now, the main question that then bothered us was the magnitude difference. So if you look at the magnitudes, they are quite different, and we wanted to get a closure on why and what is going on there. So then we did an energy audit. So what we did was we took this is kinetic energy of the body. That's the two-body potential. And this is the potential because of the gravity gradient term that gives back what we are looking for. So what we then did was we computed the total energy and computed the energy only because of the pitch contribution using moon math, and then we computed the energy difference. And that told us something totally different, and that's what this is. So if you look at the energy difference plot, the energy difference was largest in certain regions of the Lagrange region, which was considered to be linearly stable. And what was happening in those regions was that there are these very marked curves. And if you look at what is happening in those regions, we note that in those regions, the evolution of the system drives the natural frequency of the third degree of freedom to be twice the first degree of freedom. And in some of them, it drives to be equal. And in others, which are, you can't see this, but there are some yellow streaks here too. The third degree of freedom is actually the difference in the first 2 degrees of freedom. So there are some interesting equilibria in the angular velocity space that actually render, that prefer the energy exchange. So they love to play ball between the degrees of freedom, and that's what was noted here. And it's actually a function of the amplitude as well. So if you look at this size, which is the smallest amplitude size, this is the parametric plot of the same curve with different initial conditions for pitch oscillations. You start at 4 degrees of freedom, the streak is much narrower. Most places it becomes broader, and the energy exchange regions increase in magnitude. And this is another plot where we actually go further. We don't now assume any gravity gradient potential. We actually use a full, this is a 40-40 kind of a model. It's a point mass model. And for the point mass model, we have actually 16, for the cube approximation, we have about 16 roots that have different stability properties, which we can actually analyze individually using the tools that we have developed. So conclusively, we noted that gravity gradient satellite is not chaotic, and there are conservative principles, and which we could actually use quantitatively to look at how these energy exchanges happen. And these kind of analyses were possible because we were informed by mechanics. So if you look at how mechanics of the system changes, then we can actually do a lot more work. Now, the problem with using these kind of, with extending this method to analyze these arbitrary mass distributions is that there is no clear potential like this for arbitrary mass distribution. So there are infinite terms in there, and it's very difficult to find, even if we use classical or these parameters, it's very difficult to have a systematic process to write the additive equations using that. So what we are going to go look at next is use semi-analytical tools. So we have, we want to use Hampton mechanics to do this, to repeat the same process, where we can actually automate the generation of these analyses and look at how equilibria move around by addition of different terms in the gravity gradient. So, do I have more time?
Not really. You want to keep on schedule.
Okay. So let me stop here and take questions. I have another few topics, but this is a good place to stop and take questions. This is a lot of material, but I just want to give you an insight. So it's very important sometimes when you have discrepancy in either numerical results or in analysis, to go back and ask a fundamental question, and that's what we did here.
I have a fundamental question for you.
Sure.
I see essentially the resonant frequencies lining up in multiples of each other, and that give an opportunity for these exchanges. But what is the physical mechanism? What is the coupling mechanism that triggers the exchange event?
The coupling mechanism is the cross-coupling term, John. That, yeah, it's that QQ dot stuff. Let's go with the full equation. If we look at that guy,
Yes.
that's how they talk to other people. Or this guy. This is the stiffness, and this is the crosstalk, basically. So these that crosstalk happens through the crosstalk in. This is revealed in CRPs, and it cannot be easily pinpointed in 3 to 1 or the angle 3. So when they have these upper dimensional equations, they immediately linearize, and those can drop out. Can't see that.
So it's been a while since I've been on this, but I'm going to try to summarize it in my own part, and then tell me I'm wrong.
Yes.
So the conclusion that this is not chaotic motion is due because you can reduce the problem to a finite set of frequencies and not a broadband frequency response. Is that correct?
That is half of the story.
Okay.
The other half is that it was a wrong question to begin with.
Okay.
Asking for a chaotic system makes sense if the degrees of freedom are contained. In this case, they are not. There's a channel of energy exchange with the other part of the dynamical system. So, for example, if they have a double pendulum, our pendulum is chaotic, but it's a conservative system. So, if we look at a level set, the chaotic behavior happens only because we are isolating one of the links and not looking at what is happening to both of them together. So if we look at both of them together, it's not really, it doesn't exhibit unexplained changes in amplitude because it is trading off. The swinger is pumping energy into the swing.
Right.
So that's really what the big good story is, that we don't have any unexplained dynamics. We have both degrees of freedom.
I'm wondering if this energy exchange is like the dynamics which we see in the elastic pendulum.
Yes, it is exactly the same thing. But the elastic pendulum is more difficult to draw a direct analogy because the elasticity is an including the freedom form. Here, it's a finite degrees of freedom, and they force each other. It's more like several different masses connected by keys.
Yeah.
And they basically, one of them moves, and if the other one does not move until this guy has excited sufficiently enough, right? And that's what really the cross-coupling terms do in some sense.
There's a paper by Kinoshita written in the early 70s on the finite two-body problem where you maybe something even bigger than the moon and
Right.
five still
Right.
bodies. There, the attitude motions are coupled and the relative orbital motions are coupled, so you can complement all of the degrees of freedom. And in some sense, standard gravity gradient problem, the Earth's gravity field, if you're not in the equilibrium position, is working on you.
Yeah.
And infinitesimally, you're working on the Earth, but it does do it.
Yeah.
So there's something going on there, and I wonder if that's part of it. But I talk about the problem, but it's kind of one-way work.
Yes.
Because the Earth is so big.
That's right.
Small.
For the roll-yaw parts of the degrees of freedom, they are not as inertial as the Earth, so their potential changes. And that's what is,
Well, that's fully together.
yeah. And the other part of the story is that it was very difficult to do energy audit because two bodies so big. This is not even machine precision compared to the area over there. So we can't really use traditional energy, methods
For that reason.
for that reason. Two bodies is huge. So the other aspect of that is that's exactly why we wanted to investigate this problem. So if there is a chaotic behavior in the attitude, that's going to backcouple into the orbit, because especially in long term. So if you want to study these long-term evolution of hammer objects, you want to be aware of this attitude dynamics, because they go through the upper atmosphere, and modulation will change their evolution. Keep tracking them more regularly, they come back down. So that's why we do this. All right, thank you.
Jain. His presentation is on stochastic reachability analysis for the hypersonic re-entry problem.
Thanks, Jason, for the introduction. I have done this work in collaboration with Dr. Singla and Dr. Patel. So first of all, I will give you a brief introduction about the hypersonic flights. So we all know that the guidance and control of hypersonic flights present significant challenges in terms of onboard processing and accommodating uncertainties in state as well as control variables. So computing reachability flight intervals are pretty important for the safety and performance of hypersonic flights. So numerical results are numerical approximations are necessary to compute the reachability sets for nonlinear systems. So main focus of this paper is to represent reachability set as level PDF of a system's state at a given instant of time. So let us consider a general nonlinear system given by this equation, where xk plus 1 equal to f of xk plus g of xk times h of uk, where xk is a n-dimensional state and uk is a n-dimensional control input, and u represent the whole set of admissible controls that we can apply to that nonlinear system to get the reachability set. So mathematically it can be written as this equation. So what I mean to say is that let us consider initial point, and we for computing the Monte Carlo reachability set, we apply a control input. So we applied n control input to reach at first time step. So at first time step we have n states. So applying again n control inputs to each state. So you can see that we have n square states at second time step. So again applying at third time step we have n cube, n4 and so on. So you can see that it is computationally ineffective method of computing the reachability set. So what we did is in this research is we use the convolution domain. So let us take a general nonlinear system with an affine control given by this equation. So what we did is we defined f of x as v and u of a as w, where v and w are independent variables, and the probability density of x of k plus 1 is basically given by the convolution of probability density function of v and w. So what we can now do is we can take a Fourier transform of this probability density function, so which will just become the product of these two Fourier transformations, and then for getting the probability density function of xk plus 1, we can just take the inverse of this thing to get the probability density of x of k plus 1. So what I mean to say is that, so we have two probability density functions, and we represent them in as two histograms, and we need to find the convolution of two histograms. So what we take is, we take the Fourier transform of these two histograms and then multiply each other, and then take the inverse Fourier transformation to get back the PDF of xk plus 1. So that methodology is applied to the simple Dubian car model, and where x, y, and theta are the state variables, and v and w are the control variables, and these are bounded between, velocity is bounded between 10 meter per second to 20 meter per second, whereas the angular velocity omega is bounded between -1 degree per second to 1 degree per second. So as you can see that in these three plots, the Monte Carlo reachability set are represented by dots, in purple dots, and using the convolution we have these contours. So you can see that these pretty much accurately represent most of the reachability sets are inside the contours, so which is a pretty good method. But convolution is also has some drawbacks. So if we are in one-dimensional space, we can use the 100% of the state for computing the PDF, the histogram of PDF. So while we are in two-dimensional state, so if this is the PDF of a system, so to represent that in the histogram, so we have to sample the space, and we, so for sampling the space, we have only 20%, 24% of this useful information, and you can see that it is little ineffective as we go higher in the space. So the computing histograms are computationally ineffective. So if we increase the number of dimension of states, so computing convolution itself becomes difficult. So what we did now is, instead of computing exact PDF, we approximate the PDF using statistical movement. So what I mean to say is that, so consider a general nonlinear system given by this equation, and we can write the component wise as given by this equation. So we can compute the first order statistical movement given by this equation, where we can utilize the fact that xk and uk are independent from each other. So we can, instead of computing the expectation value of g and h, g is a function of state and h is a function of control input, we can separately find the expectation of state g of xk and expectation value of h of uk, which is control input, and multiply it together to get the expectation value of xk plus 1. So similarly, we can find the first order statistical movement, and similarly we can find the second order statistical movement, and using the same thing that xk states are independent of the controls. So on, we can also find the third order statistical movement, but in this work we only considered movement up to first order and up to second order only. So how to find the expectation value? So what we did is, we used the quadrature, one of the quadrature method. We use cut 8, which is conjugate uncentric transformation 8. It is approximated up to 8 dimensional space. So you can see that as the dimension of random variable increase, we only need to, the number of points we need to use are very less compared to other quadrature method. So we use cut 8 method. So the expectation value of f of xk is given by this formula, where the wx are weights corresponding to the state dimension. Here, if we need to find the expectation value of h of uk, we can find the using these formulas. So in short, what we did is, after computing desired statistical moments at each time, we can construct the probability density function using principle of maximum entropy or sum of squares. Then to generate next PDF of next time step, what we will do is we generate samples from newly approximated density function to compute states at next time step. So since we only use the second order statistical movement, so only first two coefficients of this polynomial function are non-zero. So we generate, in short, we generate cut point from standard Gaussian distribution, then we sample our state variables, then we compute the multidimensional integral to compute the statistical order. So then we compute our polynomial series, and then we can go back to step 2. So we applied this to the hypersonic re-entry problem, where the flight dynamics models are given by this equation, and comparing this dynamic model to general nonlinear system, we can see that our states are given by h, v, gamma, theta, psi and p, and whereas the control inputs are given by alpha and beta. So we take two maneuver test cases. One is the first maneuver's purpose is to was to space shuttle re-entry with heating constant, and second maneuver purpose was to maximum impact at the target, maximum energy impact at the target. Whereas, so where here the initial states, the mean and covariance is given of the state, and the control profile is given for alpha and beta over time. So this is the mean given by that, and we applied 3-degree Gaussian uncertainty to that profile to compute the reachability set. So in this figure, you can see the reachability set of states over the time, and you can see that the purple dots are represented by the Monte Carlo method, and red line is the mean, and yellow line and green line represent the 3 sigma bound of our method. And you can see that these pretty much accurately represent the most of the points lie inside the 3 sigma bounds. So after that, we consider the close correlation between each states at different time steps. This 4 time step, T1, T2, T3 and T4. So the close correlation between the X versus V, you can see that at some of the time these are positive correlated, some of the other times these are negative correlated. So you can also see that the shape of at some of the points the shape of the dots are not the Gaussian, because here we only approximated movement up to the second order term. So that's why some of the points lie outside of the 5 sigma bound. Similarly, for the latitude and the longitude, you can see that almost most of the points lie inside the 5 sigma bounds. So for the second maneuver, similarly we have the control profile. We applied the 3-degree Gaussian uncertainty to that control profile to get the reachability set of all the states at different time steps. So these are the results for the second maneuver, and again the Monte Carlo reachability set is given by purple dots, whereas that represent the mean, and 3 sigma bounds are represented by yellow and green line. So you can see that most of the points lie in the 3 sigma bounds, and we also consider the cross correlation here as well between different states at 4 time steps given by these. So the cross correlation between H versus V, you can see pretty much inside the 5 sigma bound, but here you can see some interesting thing again, that since we only approximated up to second order movements, so some of the shape is non-Gaussian. We were not able to capture that non-Gaussian behavior of the PDF. So similarly, the longitude and latitude cross correlation is given, and you can see that it pretty much lie inside the 5 sigma bounds. So in conclusion, we developed a computationally effective method to compute the reachability set. We exploit the use that control and states are independent of each other, and we developed the numerical results which clearly represent that it is pretty much good approach to approximate the reachability set, and it provides a trade-off between computation and accuracy. We can control the number of statistical movements to be computed. Further, you can see that it can be extended to open loop and closed loop system. So soon we will inculcate the third order movement to see the non-Gaussian effects also of the PDF. Thank you very much. Any questions?
Can you switch to the slide just before the result? One slide before. Yeah, I'm not a little bit confused. So what is the PME and the SOS?
Oh, PME is the principle of maximum entropy, or SOS is the sum of squares. These are two methods with which we can compute our PDF from the statistical method.
Okay, thank you. Just no comments. If you want to use those abbreviation, it might be better that you mention the full wording, so the audience know what you're referring to.
Okay. I think when you're explaining your result, if you go back to your two maneuvers, yeah. Can you explain what are those red lines correspond to, and what was your controller constraint?
So we took this maneuver from these two papers, where the red line represents the optimal control profile for the space shuttle re-entry with heating constant. So it minimizes the heating constant if we follow this red line.
Yeah. And what was your control constraint?
So our control constant is we applied 3-degree Gaussian uncertainty to that optimal control profile. And
There are only two controls.
yeah, so alpha.
So there is no 3D.
We applied 3-degree Gaussian uncertainty
Okay.
to
So you meant to say 3-degree variation
around
with the optimal control profile at each time.
The next presentation is Khushboo Patel. Her presentation is titled Precision Landings on the Moon Using Particle Storm Optimization and Lambert Charting.
Good morning, everyone. My name is Khushboo. I work with Dr. Spencer, and today's topic for me would be landing precision landing trajectories on the moon using particle storm optimization and Lambert charting. So as you we plan to go back to the moon and eventually to Mars, it becomes really necessary for us to develop the research with existing advanced technologies. They go hand in hand to accomplish tasks within constraints, like minimum fuel trajectories. You have to do this in a certain amount of time possible, depending on you have crew on board or no. My thesis or my research is focused on developing the landing trajectories on the moon. Why is this important? Because as we all know that moon's atmosphere is really thin. It's called the surface boundary exosphere. It has the less number of molecules compared to Earth. And so, because the atmosphere is really thin, our entry, descent, and landing processes becomes really sensitive. Thus, we're developing landing trajectories using particle swarm optimization, using Lambert targeting. Say we want to land on an interplanetary surface without crashing. Now, we start at a certain point, which is P1, according to the algorithm in Lambert, the Lambert's algorithm in Curtis. We start at some point P1, and we want to land on the moon. However, if we have to develop a habitat on the moon or Mars, we need to drop off payloads close to each other, or say if we miss an opportunity to land at a selected landing site, we don't want to land, like, depending on how you're maneuvering, considering this is all auto landing procedures, you don't want to land too far from your R2, or if you have two landings scheduled in a certain period of time, which is really quick because, like we talked about, we have a thin atmosphere, it becomes really necessary for us to have a precision landing algorithm. And so the goal of my thesis is to use this particle swarm optimization to find a possible combination of the variables that defines the trajectories. So we are starting at a certain latitude and longitude around the surface of the moon at a particular altitude, and then we have a landing site, which is why we're using this optimization to find optimal solutions to this landing site. We also know that PSO has been used for many other applications, for in aerospace, for unconstrained or constrained optimization. It's also been used for a lot of impulsor transfers. It's also used for multi-stage launch vehicles. Now, before I start into the details of how we're applying particle swarm optimization to Lambert, we start with some initial conditions. We start with a moon inertial reference frame at an altitude of 100 to 200 kilometers around the surface of the moon, which is our P1, and the position vector is defined through P1 with respect to the moon-centered initial frame. We're only our search space only includes the circular and elliptical orbits. We're having some ranges for inclination and the other classical orbital elements. Just for calculation purposes, I've selected the date to land. It's called 7th April 2020. And other, my P2 is defined by latitudes and longitude, and this is in a moon-fixed frame, so it rotates with the moon rotation. Other assumptions with my calculations are we're starting with a circular orbit. There's no major plane change maneuvers and other perturbations. Everyone is familiar with the Lambert's algorithm here, but I would like to shed some light on the PSO application to Lambert. So our cost function, which is what we're going to be minimizing, is our total delta V. That is a combination of delta V1 and delta V2. And we have the Lambert velocities applied to the total delta V. So we're using Lambert. The V1 spacecraft is retrieved from the point P1, which is associated with the R1 vector, and the V2 site is calculated using the latitudes and longitudes of the site, which remains constant. For the particle swarm optimization, we do know that we have a particle. It's a swarm of birds that fly in motion together without colliding with each other, and they land at a certain location, fly back together, do whatever they need to do. And so, like, if you imitate that to spacecrafts or dropping off payloads, we're having a multiple solutions to trajectories that we're starting with. Each trajectory has some information, xi, at certain instantaneous time t. The new information is something else. What is this new information? PSO, which was introduced by Ibn Park in 1995, it says that there's an inertial coefficient that is associated with an individual particle information. There's the social particle coefficient, and there's like a global coefficient that includes the stochastic, which is the global, and the regular, the swarm information. This is the individual particle information, and this is just the previous information, like an inertia. So applying to that for our problem here, we're changing the classical orbital elements, which is our 7 vectors search space, 7 variables, and that's our search space. We're updating each variable with some new information, and the new information is defined by the cognitive coefficient, which is the individual particle information, which is its personal best. This is the global best, which is the stochastic coefficient. This is scaled according to delta V. So here's where the delta V comes in to play for the particle swarm optimization. To better understand the process that we go through for these, the PSO2 Lambert, we're starting with a random population of random 100 trajectories that are generated in the range that we specified earlier, so 100 to 200 kilometers altitude, the regular range in the northern hemisphere of the moon. So starting with a certain combination, 100 trajectories having a random combination of A, semi-major axis, AEI, omega, theta, and the time of flight. The Lambert gives 100 total delta V's. Now what our PSO does, before we apply PSO actually, we select the 10 best delta V's. What is the best? We want a minimum delta V, right? So we get a total minimum 10 total delta V's. We apply the PSO equation, which is we update the particle information. So you're updating the A, E, I, omega, theta, and time of flight, as well as the argument of periodics. Once you're done doing that, you have 10 new particles. We want to make this algorithm in a way that our generation of the second population is dependent on the first generation. Thus, we use these 10 particles and the information of these 10 particles, so the classical orbital elements and the time of flight for these particles, the 10 new trajectories, and use that to create the 100 new trajectories, 10 to 100. They have a uniform distribution. Since this is a stochastic algorithm, everything is generated by random functions. Thus, we have a new swarm, a new population, which is based on the first population, and then we apply that to see where we have the total delta V's. We find the minimum 10, and then we sort the 10, and then we apply the PSO. We repeat this process until we get to convergence. The goals of my research are: you have to minimize total delta V. You define 10 possible combinations of the classical orbital elements and time of flight that pass through the landing site, which is our point P2. I would like to mention that the combinations of the classical orbital elements are associated with point P1, which is our starting location for the descent. We're also applying this to to minimize total delta V and the time of flight, but that's still a work in progress. Right. So going into how we have the evaluation of fitness through generations, we start with a certain swarm, this total delta V for the first generation, which goes into after 40 generation, we have a new population. These are 100 new trajectories after 40 generation. We all see that in the beginning, they go from a range of like 16 kilometers per second to 2 kilometers per second, or like 1.8. But after like a couple of generations, it goes through like in the range between 1 to 8 generations. It's still all over the place, but if you look more in detail with this diagram, it's the total function with respect to generations. After 40 generation, it follows a pair-to-frontier graph. And this is for a landing set of 20 degree north and 20 degree east. Also note that I'm trying doing this for a different landing site, and the results will be followed later on. So the minimum delta V that we get here is like 1.2, which is almost around like 30% to what we had at the beginning, at the starting of the population generation and PSO. I also wanted to investigate how the PSO and Lambert go together with the classical orbital elements for P1. So it has a normal trend, it's decreasing obviously, so you're making sure you're not going out of the surface of the moon, but you're actually landing. The inclination and the right ascension of ascending node showed some interesting behavior when I researched through a lot of like different landing sites. So depending on what landing sites I choose, the range of these two variables fell apart. Like we have like 0 to 50 here, 0 to 20. When we go further, say like 10 degrees north and 76 degrees west, it went further, so like 40 and beyond 40 degrees. For a landing site of 76.225 south and 8 degree west, I found that the delta V, the minimum delta V, goes to even lesser value. It goes to some 33% change from what it was initially. Thus, I see that this one behaves more, it behaves according to the pair-to-frontier even better. There's other trajectories that do fall, and there's other generations which does have values around, but most of them have like values closer to 1.6. And these are the classical orbital element behavior for that landing site, the 716. Now, I found that if we flipped the coordinates, so let's do 10 degree north and 76.225 west, I found that there was a significant change in delta V that we found, the minimum total delta V at the end of 45 generations. Both of these results did converge to around after 40 generations. All of these new trajectories that were found, their combination did not show a specific pattern, like a combination of these 7 variables, the A, E, I, beta, omega, argument of periapse, and time of flight. There was not a specific pattern, but if we see the next slide, the ground tracks, I found that a lot of these trajectories pass through our landing site, which was not the case when I was researching this and we ran this on other landing sites. At the poles, we had divergent results. The results did not make sense. We started with certain trajectories, which this is at the beginning of the first generation, and this is at the end of the previous generation. Which is why I picked a certain landing site, because it showed a normal. I was really excited to find this result, because for a lot of these landing sites ranging from 10 degrees to 20 degrees and landing sites between -76, -20, so it's like the west and a latitude of around 0 to 10, it showed a specific behavior. Before we go into details of that, I also would like to mention another landing site that I researched. It's the ARGo 11 landing site. The coordinates, the landing dates remains the same. The coordinates are 0.674 north and 23.472 east. The delta V total was larger compared to other landing sites that we picked, but it still showed the normal, the optimal behavior that we have been talking so far. To provide a result summary of my findings and what I've been learning so far, I found that a lot of these landing sites, starting with the 8-degree north, which is one highlighted in green, I found that the location of P1 that was calculated after 45 to 50 generations of PSO with Lambert, we found that all these trajectories fall in a range which is closer to our P2, which is our landing site. Same goes with the 20-degree north and 20-degree east. The delta V change is better in 20-degree north and 20-degree east. We have a 33% minimization. Like it starts from an initial delta V and goes to a final delta V, like the optimal delta V. There's a change of like 33%, so they're reducing the delta V by 33%. This one was like around 2%. You're starting from like 1.6 some, and your final is 1.67 kilometers per second. However, the ground track for these showed better results than that. This is still a work in progress, so I would not like to make any final conclusions on these. Other landing sites, if we flipped the coordinates, so 76 degrees south and 10 degrees west, the behavior of ground tracks was not that great. However, our delta V versus the generation graph, the parallel function did show the convergent results. So while I'm still researching on ground tracks and the landing sites, definitely for the Apollo 11, it does not fall in the range even closer to our landing site that we begin with. So while we're still researching this, I would like to provide some conclusions that we can have multiple precision landings on lunar surface using particle swarm optimization, if provided we have more results and more theories to support this. I found that after 40 to 45 generations of trajectories, my star space is still 100 to 200 kilometers, and the delta V calculated was in the range of 1.2, 1.69. Again, this is the and PSO can be used to optimize landing trajectories on Mars, provided we have atmospheric models included in the PSO. With this, I would like to conclude my presentation for today. I would like to thank Dr. Spencer for guiding me and giving me this opportunity to raise the thought. And I would also like to thank my friends. My parents were actually watching my presentation live, 7,626 miles away from home. And I'd like to thank everyone who be present here, listening to my presentation. And at this point, I would like to take some questions.
Sorry, I don't have much to watch now. 4 to 5 generations is not a lot for PSO. And are you certain that it's not just stagnating at 45 generations and doing things to stagnate it and have it proceed to better result?
Yes, so I've tried this doing it for 100, 200 to 300 generations too. However, as I mentioned before, initially when I start with, I have 100 by 7 matrix, so it's really hard to compute it. It follows a normal behavior even after 45 generations, and it basically, the behavior of A, it kind of crashes down like you remember how we're searching for values of A2, so it crashes down after like 7 meters, like it goes through like 1,600, 1,500 kilometers to the 7 major axis of that with respect to the surface. So after like 100 generations or so, there was no point, like after 60, there was no point in running these iterations for a while. So.
But there is this phenomenon called stagnation where it appears to converge, it hasn't really. So I'm asking, have you done anything to explore how you move it from the stagnation condition and allow it to continue to make progress?
Not really. I think I haven't like used a certain conditional statement to like basically do that. I'm trying to see like its own behavior naturally how it works.
We haven't got to that point yet. The system by having so many variables in it, you've got a huge search space, 7-dimensional search space, and we're looking at perhaps trying to cut that down and seeing if we can then go out to further generations. We're having computation problems right now.
So are you assuming that you're only performing one maneuver to create the trajectory and because they're going to have some sort of like ballistic collision?
Mm-hmm.
So
Not really.
Those two maneuvers.
was that?
It's a maneuver to start and a maneuver to stop.
So the maneuver to stop, are you just assuming you're going from whatever velocity you're at to zero?
Yeah, to the velocity of the landing site.
How long does it take to run one iteration?
One iteration? It's pretty quick. But to run 50 jumps, it takes like a good 10 minutes for the amount of calculation. Just because it's a 7, like counted by 7 matrix that I'm computing every time, and I'm performing Lambert on it, like time and again, it's a lot.
So you said for the graph to the right? You said that if you go further in the iteration,
It
crashes?
Yeah.
or don't you have constraints on this?
We do. It's like a range, but you remember like how, depending on how our delta V increases, like I don't have, while I'm generating the new generation, I have a range for A, but I don't have range for A to like stop it. I'm trying to see a natural behavior where it stops.
I mean, the search domain,
Yeah,
you
so
have
like,
the mean value must be like the radius of the mean.
yes. So once I go beyond the radius of the moon, I kind of like
What
those
is beyond that?
like you crack, so 1734 kilometers, 7 major axis of 1734.
They are the radius of curves. The radius of
Radius.
curves.
Because maybe the first iterations are to lower A, and then A will be constant, and just
You mean the first,
like following what Dr. Moulton was saying, maybe like getting lower values for A will lower the probability, and then when you reach the level for A, the algorithm will like adjust all the values.
we did have a problem at the beginning with the A values going too large or too small. So for that, we changed this coefficient depending on what values or the combination of the coefficient values that you choose. Your change in A can be controlled. So I mean, I'm trying to implement a conditional statement, but then that would not make it. That's what I think that Yes.
Quick questions. Are you accounting for lunar terrain variations? Because there's a very significant, mountain craters that can affect your where you actually land relative to the radius of the moon, and then also any human factors about deceleration, or the terrifying thing that you've got a delta V that starts when you're, 100 meters above it and won't go down as, big,
Yeah.
10Gs around.
So very interesting because when I first started with this research, I was looking into a lot of like terrain features and the LCAD software, how they go through the image processing and how they were basically evaluating the terrain. But for simplicity of the calculations and stuff, I haven't included as well as the craters, because I'm just starting at an altitude of 100 kilometers about the surface of the moon, assuming that this is like a perfect distribution.
We have a 15-minute break now. Back at 10:05. Dr. Chris Scott will be.
It'll converge to the same thing.
And try to understand
No, I thought I was going to be here
So, I was wondering, you started
Yeah. It'd be great if these buildings were
Actually, Dr. Rose suggested we do journals instead, and Jason was like, nah, we should do bagels. Like, no more filling. Really? Yeah. Never known anyone to turn down donuts.
Yeah, that's always and what we may end up doing is fixing T1 and fixing T2 and preparing flight. That's right. That's the next thing we're just trying to reduce it. Yeah, instead of one-dimensional search space, which always changes one variable. And looking to see if you can find what's the best time to flight.
very nice fake plants they have in here. Or at least this one. Yeah, this one is too. Funny they have the fake plants by the actual real sunlight. If it ever reaches back to this corner, it may not. The corridor here is normally pretty dark. Or the helicopter people go up the street. Sure. I could get commander
Give you the
rely on cost.
Create one for the other, but you can't get sweet spot in there. Like, get the best
Really? I was gonna say, like I could have just said no. Guilt trips people and shameless.
You were using Lambert's problem beginning to end. It's kind of you're definitely sort of too nervous.
Well, didn't have a microphones on, but it knows somehow.
Oh, she used the Lambert algorithm to choose the
Every night,
I decided, I told her rather than rewrite your own, you choose. So that's, let's see what's the best way to get it. What's the best way to get it? Where do you get it from?
Compared to my first one.
That's the best way.
I'd probably say it's like I'm learning so much every day. And like when I first started using
I always get the
Burritos are all I have.
You can't make it, right? No, I can't. I'm gonna just
You come to the game,
Sure, yeah. I'm definitely
Yeah, my daughter is baseball. She wants to play. I say cricket.
You do the consider common folder.
Yes.
In some cases, if the system is fully absorbed, consider parameters to be estimated in the common folder. So, three interesting cases. One is you absolutely consider parameters and do not consider their build. One solution, which will probably be optimistic in terms of variance estimates. Two is you consider it. And three, you do a full state
I was up pretty late. I was just banging my head on freaking having multiple braces that are spanning multiple lines. I was a little late. It was getting too late, so I wasn't seeing where that's on there. I think I got everything.
Feels like that.
And I this week I
I made a new scheme because I just want to make sure that you're growing. There's two. The way I was doing it before, I was assuming that the velocity was rotating. Okay, that's the body frame, but that's not really that. So I changed this, the velocity vector is fixed in the inertial frame, and then it rotates, the body frame rotates. So I fixed it, I added that to the slide. Well, I actually go with the first time I wanted, and I have another company.
Certainly better than not.
There are people who will like this.
I've never like, I don't know if it's so.
You shouldn't need them. You do the lower level. We're talking like about 45.
Yeah, definitely. Look at that. Yeah. Thank you.
I think people just I think you're just going to know you'll get better usage.
I had those examples to show.
I'll take it.
There's not going to use you, right?
Still your seat.
So there's some so if there's something you can take, right, you know we can pop it. So like it could have done something. You don't know take the building apart.
Yeah, that's so bad.
Oh, no. There we go.
Okay, I think we'll go ahead and get started again. I want to introduce our next speaker. It's Dr. Chris Scott. Chris is an alum of this department. He's one of my PhD students. Graduated in 2010 and has been at Johns Hopkins Applied Physics Lab ever since. And he's going to talk a little bit about some of the activity going on with the Dragonfly proposal. Yes.
Thank you. Okay. So, Dragonfly is a Frontiers class mission. So it's a competed NASA mission. So there's the Discovery class, which is around about $500 million, and then New Frontiers is a little more expensive. It's around $1 billion, a little north of $1 billion. And so we submitted the Dragonfly proposal. So it's 2017 now. And we were selected out of 9 potential proposals across the country. We were one of 2 selected. The other is called Caesar. It is a comet sample return mission being run by the Goddard space flight mission. That's an exciting mission as well. But I'm going to talk about Dragonfly, and I like to give credit to people who have contributed. Jim McAdams, before he left the lab and before I participated in this program, worked on Dragonfly as well. So, list of authors here. So we have APL mission designers. I don't know if anybody knows or remembers Mark Zimic. He's also an alumnus. Doug Adams, he's a pretty brilliant guy. He's a system engineer at APL. He's originally from JPL, and he designed parachutes on a lot of the Mars landers. Ralph Lorenz is probably the world expert on Titan science, and he's written books on it, in case you're interested. They're pretty interesting. I read one. And then we have a slew of JPL navigation engineers. Shyam Bhaskaran, I don't know if you've ever heard of him. He does a lot of small body applications.
He's actually a classmate of mine.
Was in Colorado, you know. Dwayne Rock, he's a working on Cassini, Voyager. Radhika Marchesik, and some of these young people, they're good as well. So I've learned a lot from them. I'm not a navigation engineer, however, I will speak with a false sense of confidence about navigation work. But if I don't know, I'll tell you if you have a question. Okay, I'll move on. Oh, by the way, please, I have plenty of, I think that I have plenty of buffer on this presentation, so I want you to understand what I'm talking about. That's more important to me than getting through the slides, so please stop me, ask me, be interactive if it's necessary. Okay, let's talk about Titan. Titan is an incredibly interesting place. It is Saturn's largest moon. It is not the largest moon in the solar system. That title is held by Ganymede, which is slightly larger. It is, volume-wise, almost Mercury's more massive. Mercury is denser, but bigger. It has a rich organic atmosphere. So when you think of Titan's atmosphere, you're on the surface and you look up, the collective mass of that atmosphere is 10 times more than Earth's atmosphere. And so, and because it has a lower gravity than Earth, this atmosphere is extended farther out into space. And what that means for us is that if we want to send something to Titan, we have this thick, pillowy atmosphere that we can send entry vehicles into, which means deceleration profile is a lot better for hardware. It has the atmosphere is mostly composed of nitrogen, just like Earth, but it has methane as well. And this methane, there's a methane cycle on Titan, and it's much like how water is on Earth. So water evaporates, rain forms into rivers and lakes. Well, the same thing happens methane on Titan, and there's been other missions proposed to explore these methane lakes. Titan, we're not going to explore the lakes for this mission. So it has water as well, at least they hypothesize that it has. A lot of these moons have subsurface oceans of liquid water, and these are really interesting to scientists because, you look at hydrothermal vents and things like that on Earth, there's life there. These organics in the atmosphere, methane is an organic compound, and the solar energy from space comes in and, again, I'm not the expert at this, I won't claim to be a scientist, but it breaks down these compounds. There's a lot of organic chemistry in the atmosphere, and they believe that it resembles what conditions were like in the early Earth. So understanding Titan may mean understanding our own origins, and so it's a very, very compelling place to visit. And here's the, reiterating the point. Because of this thick atmosphere, the mission design itself is vastly simplified. So you think of the other missions to these outer planets. I'll choose Clipper, for example, or Cassini. When you get to the planet itself, before you even visit the moons, you have a very, very large maneuver to stop yourself, basically slow down and go into orbit about the planet. But we don't have to do that because we have this big pillowy atmosphere to absorb all this energy that we've gotten from launch and from our inner solar system cruise. So this not only simplifies the mission design, it makes trajectory designers' life a lot easier, but it simplifies the spacecraft system itself, making it cheaper and perhaps fitting into a New Frontiers class mission and not a flagship mission. Okay. Okay, so let's talk about, so this is the quadcopter concept. Really neat. I talked about the thick atmosphere. What that has a direct relationship to is the power for hover. It's 1/40 of the power to hover on Titan, the one that's on Earth, and it's because of the thickness of the atmosphere, and it's because of the gravity. It's 1/80th of the power required to hover on Mars. So it's a lot harder to fly a quadcopter on Mars than it is on Titan. Also, you think, okay, flying a Titan, quadcopter around on Titan is pretty risky, right? Because you probably maybe crash one on Earth. But there's really no sustainable winds on Titan. It's far away from the sun. You don't have the heating up the atmosphere and causing tornadoes, things like that. So it's a very benign place to try to fly a quadcopter, and that's a good thing because we don't have a lot of power available. We have an MMRTG that powers batteries. And it flies approximately once every what we call T-Sol Titan day, which is about 15 days. So this aspect of the mission is really interesting. It's super interesting to use terrain relative navigation. If you don't know about it, you should read about it. And I'm really jealous of the engineers who work on that, by the way. They work right down the hall for me, and I hope to be involved with that at some point. Okay, so here's just some eye candy for you. This is after it's entered the atmosphere, released its parachute. Sorry for the glitchiness.
It's atmospheric disturbances. So.
Yeah, right. Right. I lied about the wind. That's the wind. So, it's cool to look at, but this is actually how it's going to land. It's not going to land on airbags or anything. It's going to be released from the hot shell capsule. That's a high gain antenna in contact with Earth. It's not that bright on Titan. It's actually closer to what conditions look like at early dawn on Earth. There is enough light to see. Okay, so this mission, I think a lot of people look at this mission, and especially mission designers who work on complicated boards, stuff like that, and think, okay, how complicated can this be? I'm not going to try to prove to you that it's complicated. That's not the intention of this slide. The intention is to tell you that there's many, many design loops that you have to work with when you're designing a mission like this.
And I'm going to start walking you through this, and this is where, I don't know, if you don't understand what I'm saying on this slide by the end of the presentation, have me walk back or talk to me. So the first thing you do, the first thing that we did, I'm not saying this is the best way to do it, this is what we did. So you start with a blank sheet of paper and you say, okay, how do I get to Saturn? How do I get to Titan? The best way to get there. Generally speaking, you do some sort of broad search. There's a lot of ways to do this. Like I said, we did a broad search. And the broad search results in a bunch of ways to get to Saturn, a bunch of ways to get to Titan. After you do that broad search, you say, okay, just because I can get to Saturn, does that mean that I can get to Titan the way I want? I mean, I did reference this big, thick, pillowy atmosphere. However, it's pretty easy to come up with a solution that is infeasible from an engineering standpoint. Comes into the atmosphere too fast, landing sites that are not scientifically interesting. So you have to really take your solution space here. So you can think of this as a set, a big solution set. And each design, each member of this set has an entire set of possible entry trajectories. So this is a continuum. It's a complete continuum. And you have to basically sort this out. I'll go through a slide to kind of walk you through our thought process. But what you get out of this process is, I'm calling it a CAS, but it's really a lower fidelity solution. So the idea here is use the lowest fidelity models that you possibly can to describe the system. You don't find a solution, you find the best solution. You prove it that it's the best solution. Once you have the best solution, you have more work to do. Okay, so here's the summary of, I forgot to mention this, but here's a summary of the constraints that we had to work with. You have, you can't go too low when you fly by Venus. You can't go too low when you fly by Earth. Things like that. Pretty standard stuff. Deceleration, we want to keep ourselves under 12 Gs. Which actually isn't very constraining. We have heat flux constraints on the aeroshell. And we also, one of the big drivers here is when we get to Titan, we want to have 60 hours to talk your phone home, basically. Because you don't want to get to Titan and then not know if your lander has landed safely. So what we do then is we take this very, very low fidelity guess. We go into our multiple shooting optimizing environment. We use Cosmic, that's a JPL developed piece of software. It's based on the Monty tool set, which is used to navigate every single mission that JPL is currently flying right now. So it's trusted, it's tried and true. You can use other things, you can use SDK, use FreeFlyer, or you can write your own program, which I would encourage you to do at some point. I don't know why these are screwed up. Sorry about that. Okay. So now once we have, we have a trajectory going to Titan. However, we haven't modeled anything about the atmospheric entry. So we go to our colleagues at the Langley Research Center, and we hand them an initial condition coming into Titan. We give them two pieces of information. First, the time we reach Titan. The second, and the only thing that matters, is the three states of the V-infinity vector coming into Titan that completely characterizes the entire entrance space. They take that entry condition and they use their very proprietary Post 2 software. This is, I think they use, it's a legacy piece of software that's used for atmospheric entry on a lot of missions that we use for shuttles. So anyway, so we hand that to them. They modify, so they take that piece of information, you can think of that as an invariant. They hold that invariant constant, and so by holding that invariant constant, so it's Titan at the same time, same direction. What that does is, first order, it holds our interplanetary trajectory constant. So when we try to piece that thing all together in a higher fidelity model, it sticks together. It's almost a what would you call it? It's a given that the trajectory will converge. So they modify that. They model parachute deployment, everything they need to model the heating of the aeroshell, and they hand us back a state about 5,000 kilometers from the center of Titan. hit that state, your high fidelity model, we're going to land where we want. Okay, so now we have that. So we have a trajectory that goes from Earth all the way to Titan, lands the way we want it. However, we're carrying an MMRTG. Oh, we still have to navigate, but we're not that way. But yeah, we have an MMRTG, and people are very concerned with giving people a radiation shower. Things go wrong. I don't know if this is an overly. It's what we have to do. Let's just put it that way. You need those soft goal. We detonate nuclear weapons in the atmosphere, just like that. We're still alive. Anyway, we got to keep it from hitting her. And to do that, we do what's called a biasing analysis. And what we do, we have to make this is a self-imposed constraint. Eventually, the Planetary Protection Office will dictate this, but we have to prove that we have less than 1 in a million chance of hitting Earth. And to do that, you have to do what's called we call it a biasing, but what you're really doing is we have these target altitudes for our Earth flybys. And what you do is you bias your trajectory out so that if you kept flying the trajectory without maneuvers, you would miss the Earth by like 10,000 kilometers or something like that. So you can think every time you do a maneuver, you have some sort of dispersion, some uncertainty to your spacecraft trajectory. When you map that the whole way to the Earth flyby, we map them on B-planes. That uncertainty ellipse can encompass the Earth, right? And so you can think of it that way. And as you get closer to Earth, you have less time for this dispersion ellipse to grow. It shrinks in the B-plane. And I'll show you a picture if you don't completely understand it. But anyway, it's a walk-down approach that keeps our impact probability low. So assuming we've done that, assuming we can navigate it, it's a pretty standard navigation analysis. We go through that loop. Now, so we get a point design out of this. But the reality is you're not going to hit that single point on Titan. You're going to hit some ellipse on the surface of Titan. So what comes out of this whole navigation analysis, which also includes the Earth biasing, we call it an ESF file, but really it's just a bunch of states that hit the top of Titan's atmosphere. The Langley Research Center takes each one of those states, propagates to the surface, goes to software set, and you get what we call a landing ellipse. And the engineering team will either be happy with that, or they won't be happy with it, or they'll live with it. Usually they just, live with it, because you never get exactly what you want. But you get a landing ellipse, and hopefully it's somewhere safe and scientifically compelling. And when you're done with all of that, hopefully you get a nice trajectory, and we're done. Oh, yeah, and so if you don't like it, then you redo your barythermal design and start over again.
Chris, could you elaborate on how these B-planes are chosen to begin with?
Right, so
sensitive to B-plane.
Yeah, so you're referring to the biasing. So we have a process, and I'll touch on it a little bit. We have a sort of a two-tiered process. The first is that we use Lambert, which is just is a linear analysis. So you take post-maneuver and really propagate the STM variational to the B-plane. And that gives you sort of a first order, okay, I get all the statistics I need, I can prove that it's less than 1 in a million, but the delta V is usually pretty awful. And so what we do is we have like an iterative loop where we get this first order guidance, and we re-optimize it, right? And so like the previous flyby before the next Earth flyby, like takes you to your biased aim point instead of having to maneuver to it. And you iterate with that loop to check to see if it's less than 1 in a million. And I think we have some work to do on sort of the smoothness of that process. It's very manual right now, but I think it's a completely deterministic process. So I'm going to get into sort of some of the sub-blocks here. How am I doing on time? Okay. Some of the sub-blocks here. This is the result of our interplanetary trajectory research. And what you have in the legend up here is our combinations, Venus, Earth, Delta Vega. So you have the infinity leveraging interplanetary trajectory as well. And so really, it was a pretty simple choice once figured launch date, delivered mass to Titan, first order. We knew that we were going to be on the upper end of this, at least curve. We weren't going to be down here. We're not going to send a 500 kilogram spacecraft. We knew that. So we maximized mass. So we selected this VEE solution. So it launches from Earth, flies by Venus, Earth twice, then heads off to Saturn. And what you're basically doing here is you're pumping up the, if you plot these trajectories in the space of energy, you're basically pumping up the trajectories, heliocentric energy, to minimize the energy necessary for launch. Now these trajectories themselves have a lot of advantages. So this VEE is right here, and this EVE is right here. And one of the tricks that a lot of trajectory designers use to get a backup launch trajectory is they'll tack on a one-to-one Earth resonance. So you launch from Earth in a one-to-one resonance with Earth, and you come back, and basically you're on the same trajectory that you would have been had you launched a year later. So what that does is this trajectory and this trajectory, after that first Earth flyby, are qualitatively the same. And if you do a little bit of work, add some degrees of freedom to the problem, some maneuvers, you can actually make these trajectories hit Titan completely equivalently. So what I mean by equivalence is that, some altitude above Titan, call it 5,000 kilometers, 7 states are matched. You have position, velocity, and time. And that's across the primary launch period and the backup launch period. It completely locks in the entry. And spacecraft designers love this because no matter when we launch, we have a constant entry condition. And it's also operationally very simple. So you can think about, there's a lot of manual effort. I believe most of the space mission's cost is in labor. And so there's a lot of manual effort in scheduling all of these activities. Whole engineering teams stood up to rehearse what happens when you land, this and that. And so we have a constant condition. This is very, very simplifying from a programmatic point of view. Okay, so I'm just reiterating what I just said in words. Launching, hitting the same conditions. So there's two very simplifying things going on. One, we have a backup trajectory that's completely equivalent. We're getting to Titan the same way across the entire launch period. We have no large maneuver throughout the entire trajectory. We don't have to slow down at Titan. We're using that large pillowy atmosphere. So this is about this is a very ideal solution for us. Save the fact that we have to fly by Venus, which causes some thermal headaches, but in this case it's pretty benign because we're flying by Venus at a high altitude. Okay, so what we did is we took that trajectory and we actually did do some time optimization with it. So that last Earth flyby, that provides your final kick out on your way to Saturn. Turns out that there's a monotonic relationship between your Earth flyby altitude and the time length of that last leg. And we took ourselves the whole way down to our 1,000 kilometer altitude constraint that we self-imposed. If we go lower, we can get to Titan a month or two earlier. And so here's your Titan arrival date versus launch C3. C3's not changing that much, but we're basically, we cranked that the whole way down. You don't get that for free when you shorten the length of that last arc on your trajectory. You enter the atmosphere faster, and so you're upping the G loads on your shell. It turns out that was a good trade for us because we're still entering the atmosphere under our 12G constraint. Okay, so I'm going to take you through sort of the mathematical process of how we compute these spaces. We documented some of this in a paper in Snowbird, and then before that, a lot of this is documented in actually a Clipper paper because math is math, and it applies to Clipper as well. So what we do is we have some nominal interplanetary trajectory. So just as that I said that time and that incoming V infinity vector is important on Titan, the time in V infinity vector is important on Saturn as well. So this is Saturn here. So for a single interplanetary trajectory computed with patch conics, you actually, with a 1D, so you can reduce the problem to a 1D root solve, you can completely characterize the every single way that you can intersect Titan's orbit. And so that's what this picture is. So given this single interplanetary trajectory, this is every single way that you can intersect Titan's orbit. Some of them are prograde with respect to Saturn, some of them are retrograde. This is the interface velocity magnitude at Titan's atmosphere versus your time of arrival. So what you have here is this is approximately one Titan day, one Titan orbit. Titan is gravity locked. But here's, so you can come in really, really hot if you come in retrograde, and you can come in a little easier if you come in prograde. It intuitively makes sense, but it's nice to have the entire trade space at your fingertips. System engineers really appreciate this type of analysis because they know everything that's possible. So if they ask me to do something that's impossible, I point to this chart and I say, yeah, we can't come in with this trajectory at 6 kilometers per second. It will not work because it's physically impossible to come in at 6 kilometers per second. So what I'm just going to choose, this is not the entry that we chose for the mission. This is arbitrary, the landing site proprietary kind of thing. But what I'm going to show you is good enough to give you the idea. So let's say we choose this point here, around, I think it's around 7.6 kilometers per second. So now we have a single trajectory that intersects Titan, shown here. And like I said before, all we need is that time and that incoming the infinity vector. And now we're going to characterize the entire interspace with respect to Titan with the end of this slide and the next slide. But what you can get is no matter how so energetically, no matter how so if we choose this particular trajectory, just by sheer conservation of energy, at one particular altitude, we're always going to have the same velocity when we enter the atmosphere. And so this is they call them carpet plots, but this is your flight path angle at 1,270 kilometers of Titan surface versus entry velocity. And the contours you can't see here, they're not real important, but the green lines are your G loads on the spacecraft, and the red lines are your thermal loads. And there's a little kind of pink box here where I've outlined the constraints. So we're on this solid red line. We know what velocity we're entering in. We know the design space on our hardware, so we know where we lie here. We're between here and here. So no matter what we do, because of physics, this is where we're going to lie in the design space. Okay, so now let's say we're on the design space, we're where we want to be. So how do we pick a landing site? How do we even characterize what pieces of Titan are accessible? So again, we start with our incoming asymptote, and so this is a picture of Titan. I'll explain what the shades are soon. But this point right here, if you take the incoming V infinity vector, pass it through the center of Titan, and you just project it onto the surface, this is the mapping of that V infinity vector. This is the subpoint, Earth subpoint. That's important because of our time to Earth set. But take a look at this point. So we're coming in at a hyperbolic velocity. If this are on a hyperbolic trajectory, if that hyperbolic trajectory had, this is mathematically impossible to pretend it is, that hyperbolic trajectory had a radius of periapse of 0, it would hit right there on Titan. But as we increase the radius of periapse, it will form concentric circles on Titan if you take the entire space. Constant radius of periapse, you change the orientation of the same hyperbola coming in the same direction, it's going to form concentric circles. And eventually, you're going to get to the point where, because of the characteristics of a hyperbola, we know that we're going to enter the atmosphere before periapse. And so what you can do is you keep raising that radius of periapse until you get to the edge of the atmosphere. And this light line here is dark. This dark area behind on the other side here is just physically, geometrically, impossible to reach given that set of hyperbolic trajectories. So that's given one. So scientist comes and says, I want to hit some latitude, longitude in the dark area. You know right away it's impossible. Now you can take the same idea and fold in your flight path angle constraints. Flight path angle maps directly on that carpet plot I showed you before. It maps directly to G loads, and G loads are the driver here. So if you come in too steep, you break your 12G constraint. If you come in too shallow, you're not going to. You're basically going to do what you see meteors that kind of just graze the atmosphere and keep going. You're going to do that on Titan. And so that's what these this is if you're coming in too steep. So this is 0 radius periapse again. Anything here, you're going to be coming in too hot, and you're going to damage your hardware or destroy it. Anything, there's like a very thin line here, and this is where you're going to skip out of the atmosphere. We used a very crude first order approximation of when you skip out of the atmosphere. It's good enough for our purposes. But what you're left with is an annulus, and you don't see it all here. You're left in an annulus of accessible regions on Titan. So this is great, except we still have to contact Earth once we get there. So not everything on this annulus can contact Earth. So what you do, you know your Earth subpoint here. This green line here is Earth rise. So if I'm here on Titan, right there, Earth is rising over the horizon. This magenta line here is actually when you have 61 hours until Earth set. That's our constraint. So we can't be on the other side of this magenta. The red line on the other side is actually Earth set. It's about 180 degrees offset. So we know, so now we've decomposed it even more. We have a subset of the annulus. Scientists say, okay, I want to land right there. And so say, okay, now you do one more 1D root solve. So you had a set of 1D root solves to figure out everywhere where the interplanetary trajectory intersects with Titan. You do one more 1D root solve to solve your incoming hyperbolic trajectory with respect to Titan. Here's what it looks like. So here's our 61 hours until Earth set constraint. Here's all of our accessible region. And here is what the incoming hyperbole looks like with respect to Titan. And you can see that for this particular interplanetary trajectory, we're coming in at a pretty steep declination with respect to the Titan's movement. So the beauty of it is that you can almost design this entire mission with undergraduate level orbital mechanics.
Chris, I have a question.
Sure.
So why would you want to land just like a unit of your axis?
That was just an arbitrary example. So I picked this out of a hat. I'm not allowed to tell what anybody what we're landing.
Did the flight path angle constraints come from the people on post 2 at Langley?
Yeah. Yeah, right. And so that came from that map. It breaks the 12 constraint. Okay, so now that we have this trajectory, most of the hard design work's done now, but you do have to make it proposal or flight quality, and to do this we use the Cosmic software package, but at its core it's just a multiple shooting method. You have a set of controls, a set of constraints. If you have a good enough guess, you hope that your nonlinear your optimization algorithm can converge on a feasible solution. It does pretty easily because we have a pretty good guess worked out. Once you have that, you can map out your entire launch period. The trajectory is mostly ballistic. So if we had no Earth biasing, in this, our maximum delta V would be 16 meters per second. And that's even with matching the conditions of the Titan's surface. So it's almost a purely ballistic problem where we start interfering with it with our own biasing. Okay, I don't think this is of great interest, so I'm just going to skip this. Okay, so this is just how, once you have the entire launch period worked out, you take the maximum launch energy across the entire launch period because it's not constant. Take that, you map that to, these are publicly available C3 curves for the Atlas launch vehicles. So it's C3 versus lift mass. We know we're right here. It's very close to an Atlas 411. Who knows what we'll actually launch on? That's just an example. But it's classified as an intermediate launch vehicle. Okay, navigation. So here's where the false confidence comes in. We have a navigation loop. So I think the real take-home point here is that the entire LB budget is dominated by statistical factors. Statistical factors are your probability of hitting the Earth, along with all the statistical factors that you would take into account for any space mission, because you never know exactly where the spacecraft is. You never know. You never have the thrusters characterized perfectly, so you always have uncertainty associated with it. And all of those uncertainties added up make our LB budget. It's a low. We view it as a project, as a pretty routine mission from a navigation standpoint in interplanetary space. And the reason is because of the legacy of all of the missions that came before us, like Voyager, Cassini, Galileo. Now we have Juno. There's no part of MSL, there's no part of this mission that hasn't been done before. Atmospheric entry, biasing with respect to the Earth with an MMRTG, things of that nature. So we're taking lessons learned and hopefully improving upon them from past missions. This is a picture of the of what biasing really is. And if you didn't understand my description earlier, maybe this will help. So you picture one of our Earth flybys here. Now, the goal is to keep the Earth impact probability to less than 1 in a million. The farther you're away from Earth, you have longer time for that air ball to basically grow as you propagate the dynamics forward. And because that covariance will be large, you have to start with your aim point at Earth higher than what it should be. So if the spacecraft died here, it would safely miss Earth, have less than 1 in a million chance of hitting it, and move on, hopefully not come back and hit us 100 years later. Don't worry, the half-life tuning 238 is not going to be what it is in 50 years. But as you get closer to Earth, the mapping gets nicer. You move it closer and closer and closer until you hit your final aim point. This is a flow diagram of the process I alluded to earlier. So we start with our nominal trajectory design. We have a simplified biasing analysis based on the Lambert tool set, which is just basically it's a linearization of the two-body problem. That linearization gives you a delta V guess of how to hit these biasing targets. Because it's a linearization and a crude test, the delta V numbers are terrible. So you loop that through our high fidelity optimization. You hope high fidelity optimization does not break 1 in a million chance of impact. If it does, you loop and repeat. Okay, so how much savings do you get from the re-optimization? So I say the delta V numbers are terrible. I'm exaggerating. So this is the linear guess for the biasing. With all the biasing included for our nominal baseline trajectory. So with the linear analysis without optimization, you get 169 meters per second. If you go through that optimization loop that I just quoted, you reduce it to 112. Okay. This is our delta V budget. It's just there for if you're interested. I don't think there's anything particularly compelling about this, except for that we have very, very large margins. And we should because we're still in the early phases of the mission. So here's what the biasing looks like as you walk that trajectory down towards Earth. So this is the mapping to the B plane. I believe this is, so this is EGA1. So this is our second Earth flyby, just based on the way that we number it. So you start out at your flyby before the Earth and do a TCM. Here's what the ellipse looks like, the covariance ellipse looks like when you map it to the B plane for that flyby. This little blue dot here is the Earth. So you can quickly realize that you're going to get yourself into real trouble if this ellipse is oriented in a different manner or if it's closer. Because you have to keep your impact probability to less than 1 in a million. And as you you get your OD updates, and as you move closer to the Earth, in the time domain, these ellipses start to shrink and they get nicer, and you do your next TCM, the whole way down to the very final one. And this is actually our target point at Earth. This circle here is what's called the impact radius. So this is a mapping to the B plane. So what will happen is you're on a hyperbolic orbit and you're inside this impact ellipse. You're going to circle around here. It just looks differently on like that. Okay. So this is my last slide. So this gives just some information on how the orbit determination is going to be all the standard things that you have for Doppler range, double doors, things of that nature. What's important is as we approach Titan, that entry flight path angle drives heating conditions and the G load. So you do have things that we would want to hit that. Really bad things will happen if you don't do that and you don't prove that you can do that. And so what this is the 1 sigma uncertainty on flight path angle as we're approaching Titan in time. You can see these little jumps here, right? So it's going down as we approach Titan like you would expect. But these jumps here, these are maneuvers. So maneuvers inject a lot of uncertainty into your trajectory just because of the nature of maneuvers. You don't have them, like I said, you don't have them perfectly modeled. So they inject a lot of uncertainty, and then you come down, and finally we hit the atmosphere the way we want. I think our experience around 0.1 degrees, which is more than enough to safely enter the atmosphere. We have a lot of margin on that number. Okay, so this is just a standard conclusion slide, but we've done a lot of work to really, I think, characterize the trade space here. We have confidence that we gave our engineers and our scientists not only a solution, we gave them the best solution that was possible given the mission constraints. And our process is not perfect, however, we will improve upon that process and hopefully leave a legacy to people going forward, just as Voyager is seeing like something for us to build upon. So thank you for your attention.
So, assuming that the project is selected, what is left for you all to do? What are the big things that you have to do?
Yeah, so a lot of it now becomes, I think Jim can probably speak to this better than me, a lot of it becomes like the fine details to actually fly the mission, all of the interfaces. You have to have, everything becomes process control, basically, right? So you have all of these interface documents. We have to work with the launch vehicle vendor. We have to set specific requirements on the data that's passed between institutions. So there's a lot of process and rehearsals, data like rehearsals, things like that. So it's a lot of very detailed work that we have to have in phase B. Oh, sorry.